All right, today we're going to talk about projectiles. So I took a picture from my childhood hero, Calvin, or was it Hobbes? I don't know. They're both awesome. If you have not read Calvin and Hobbes comics, you should read them. So one of the running gags was that Hobbes would be home all day waiting for Calvin to come back, and so every time Calvin would open the door, Hobbes would just hit him right through it and basically make them both become projectiles. So in order for me to make that statement, I have to be able to truly define what is a projectile. So projectile, we're going to define CTILE. I can't spell today. Projectile we're going to define as only affected by gravity. Only affected by gravity. So if we include air resistance, we no longer have a projectile. We include rockets, no longer have a projectile. So what that means is if I'm going to draw a force diagram of this, then let's say I'm going to draw Calvin as my object here. So there's Calvin. Look at that. Art class paid off. And the only force acting on Calvin is the force of gravity. Okay, so everyone's like, well, what about Hobbes? Hobbes hit him really hard, so there's got to be a force. I mean, he hit him so hard, look, his shoes got knocked off. See, look, his shoes knocked off. Right here, we only have socks. All right, it's funny, trust me. All right, so he hit him so hard, knocks his shoes off, and so where's that force? Well, while they're in the air, if I want, I really could have drawn a force diagram because Calvin and Hobbes are kind of one entity right now, and they're both flying through the air. So we don't include that initial force. If we were to include that initial force, then we're saying that during the entire time they're in the air, he's still providing that horizontal force. And we know that that's not true because Newton's laws say objects in motion stay in motion. So in the x-plane here, we have balanced forces. So we have nice constant velocity. So in the x-plane, we have balanced forces, because we have nothing and nothing. And so what that means is we're going to end up with constant velocity. So whatever speed he is hit with, he's going to maintain that speed in the x-plane for all of time. Now in the y-plane, though, if we look at our forces in the y-plane, we definitely have unbalanced forces, because gravity is not being balanced out with anything. So that means that we are going to be experiencing acceleration. Okay? So, a few things that do come up with is the idea, these are some traditional physics questions, and that is, one, what effect does mass have on the acceleration of an object? And a lot of people say, oh, the heavier objects, they'll hit the ground first. You know, they'll fall to the ground. So if there were two objects flying through space, the one that's heavier, that's going to hit the ground first. Well, we're going to base all of our understanding on this force diagram and our analysis of it. So if we look at this force diagram, if we do a net force equation in the y-plane, because we said that that's our acceleration, so that's what will change. So if we sum the forces in the y-plane, that equals ma. The only force in the y-plane is gravity. It's pointing down, so negative f of g equals ma. So we do have an equation for the force of gravity, so we can replace that. So mg equals ma. So if we look carefully, we can see that mass is on each side of the equation. So mass ends up doing what? Doing what? This is time for you to guess and try and beat me. That's right, mass goes away. All right, mass cancels. So then all that we're left with is the negative gravitational field strength is equal to my acceleration. So on Earth, the gravitational field strength is 9.8. And our unit conversion, so you get meters per second squared. So that's our acceleration. So irrelevant of your mass, all objects will accelerate down towards the ground with a constant acceleration of 9.8 meters per second squared. If you were to go to a different planet that has a different gravitational field strength, like Mars, Mars has a gravitational field strength of 3.7. So there you would have a different acceleration as you fall towards the ground in free fall. The moon is 1.67-ish. So therefore you'd see an acceleration of only 1.67 towards the surface of the moon. All right? So big thing here to understand is that mass plays no role. So mass does not change the acceleration. So the traditional question would be, if I dropped a bowling ball and a semi-truck off of a cliff, I don't know why we do these things in physics, but we do. Which one will hit the ground first? And everyone's like, oh, the semi-truck, man, the thing's huge, totally gonna hit the ground earlier. No, they're gonna hit the ground at the same time because they were both experiencing the exact same acceleration. And they were both given the exact same initial velocity. So that's one of the big things about projectiles, is you have to understand it's all based on this force diagram, and that all of them will be accelerating towards the ground at 9.8 meters per second squared. Also, you need to understand this links between the forces. In the x-plane, we have balanced forces, so we have constant velocity. In the y-plane, we have unbalanced forces, so we're going to see acceleration. Now, if we remember from our forces, we used to say that the forces had to be totally independent, and that's why we have our x's separate from our y's. And since the forces are separate, the motion is separate. So we have to have complete independence between our x-plane and our y-plane. So now I'm going to represent this through some particle model, and I'm going to launch some stuff off a cliff. All right, so I need a cliff, so let's get my cliff out here. Cliff. Again, look at those art classes paying off. All right, so person on a cliff, and they're going to drop an object. All right, so we're just going to drop an object. And if we were to take this object and we drop it, then we're going to see that it is going to accelerate down. So it's going to cover more ground per unit time over and over again. Got a little more space to work with here. All right, one other dot in here. All right, so each of these dots should get farther and farther away. I feel I failed on this guy. Let's get that pen back. So there we go. Why do you keep going away? I swear it's there. All right, so it's covering more ground vertically over time. So we see this vertical acceleration. Now let's assume that he were to throw it. All right, so now we're going to throw it horizontally. So if I throw it horizontally, then that means that at this first moment it's going to be right here. But now I'm going to throw it with a nice horizontal velocity. And if we look back at our definition, our force diagram, we have balanced forces when it's in the air. So therefore we're going to have constant velocity. So whatever velocity it is thrown with, it will have the exact same velocity the entire trip. All right. So the cool thing about this is then you're saying, well, which one's going to hit the ground first? Well, the red one is when I just dropped it. The blue one, I threw it out, but still, every time it's here, gravity is going to pull it down. And so gravity's going to pull it down with this type of acceleration that we see in the red plane. So even though it starts here, the next time it's going to end up here. And then the next time it's going to actually end up here. And then the next time it's going to actually end up here. And then I guess I need one more of these. So the last time it'll actually end up here. And we can see that we have our little arc that we're used to seeing objects have. So if you look at every single point in time, these two objects were exactly matched. They were falling right next to each other the entire time. Well, that one wasn't, but I'm not the best artist. All right, so they were falling at the exact same rate. So it doesn't matter if I throw it out or if I drop it, they'll both hit the ground at the same time. And the key reason for this is because both objects had the following. They had the same acceleration. I'm going to put a little y here. They have the same acceleration in the y-plane. They also had the same initial velocity in the y-plane. Both of them happen to be equal to 0. And the acceleration were both equal to 9.8 down, so that's why I put the negative. All right. And so since they had these conditions, and they're both going to fall from the same height, that means they both have the same displacement. Now you're going to notice I'm going to put a delta y here instead of a delta x, because, well, we're working in the y-plane and the x-plane, so we kind of want to keep them separate, so you'll see me do that. So they both have the exact same displacement, which is equal to whatever the heck I call this. So let's just say y. So we'll call negative y because it fell down. All right, so all these things are the same. So if I go to look at the time, well, using my kinematics equations, I'm going to get the exact same time. Since they have all these variables the same, they're going to have the exact same velocity as well, because they're both accelerating vertically. And again, this is at least vertical velocity. Horizontal velocity is a bit different. We're going to play that game a little later. All right, so that's why you'll often hear the problem of this. Bullet fired versus a bullet dropped. Which hits the ground first? Well, as long as all these things are true, they will hit at the exact same time. Now, if some of these things are not true, then they're not going to hit the ground at the same time. Like if they, let's say our ground was not perfectly flat, so then the bullet actually fell a bit longer or it didn't go as far. There's a whole bunch of variables. But as long as all of these statements are true, that they have the exact same vertical displacement, they have the exact same initial velocity, and they have the exact same acceleration, then it's going to hit the ground at the exact same time. So if someone's like, well, I fired the bullet up at an angle, well, then duh, it's not going to hit the ground at the same time. All right? So speaking of angles, let's talk about that. So what happens when you actually fire stuff off at a bit of an angle? So that was a perfect horizontal launch, but what if we fire something off at an angle? So let's say this is my ground. That is the worst line I have ever drawn in my life. I am embarrassed to be, oh my goodness. Take 5. All right, don't judge me. Line. Okay, I can live with that. All right, so let's say we just fire something up, okay, at an angle. So we're going to launch it off at this angle. When you fire something at an angle, it has components. So let's go back to our original. We'll make the y component red. So as it goes up, it has a very high velocity, but then as time passes, it gets slower and slower and slower, and eventually it will come to a stop, and then it will actually turn around. Why did you go away? Let's go back. And that will turn around on itself and double back. All right, so it starts here, goes up, it's going to come back down. All right, so that's what it looks like if you just throw something straight up. But we're going to throw it at an angle, so it also has that x component. And remember, projectiles, and I'll draw it over here again, all projectiles have this as our force diagram. So we have constant velocity in the x-plane because we have balanced forces, but in the y-plane we have acceleration that's equal to gravitational field strength. So our entire time we're accelerating down at 9.8. That's why these get closer and closer and then farther and farther. But in the x-plane we're just going to cruise along gently. So in the x-plane I'm just going to keep covering the same amount of ground every single time. So if I were to look at this, every single unit of time, this object will cover the exact same distance. So now I'm going to put these two together and I'm going to see what really happens. All right, so I'll do that in green. So they start here together, but then they're here, and then they're here, and then they're here, and there, and then right there, and now it's going to turn around. And we're going to start doubling back on ourselves here. And this is where my brain's like, did I draw that one yet? I don't know, I can't tell. I think I did this right. All right, there we go. So now you see we have this arc, this total arc the whole time. All right. And so there's some interesting things that happen if I were to analyze this a little further. If I say this, if you notice, my initial velocity is the exact same as my final velocity here. Okay, so whatever initial velocity I happen to have, it's going to be the exact same as my final velocity. They're exact flips. My velocity in the y at the max height equals 0. But you'll also notice that the velocity x is always the exact same. And again, that goes back to the idea that we have balanced forces. So whatever speed I throw an object up with, it's going to come down with the exact same speed, but it is going to be the opposite. All right. So that's pretty much all the fundamental basics that you need to know. The bell says I'm out of time, and I gotta go teach a class. I hope that helps.